Hello everybody. In this video we'll be going over one of the sections in chapter 6 of our text entitled Chemical Composition. In this video we're going to talk about how to do the molar mass of compounds. So first I just want to make clear the connection that we have between the formula mass and the molar mass. We saw last week that the formula mass is the relative weights of molecules that can be calculated from their atomic weights. Okay, so for instance, the formula mass of one molecule of water is going to be equal to the 2 hydrogens that it has times its atomic mass plus the 1 oxygen that it has times its atomic mass, and we get out 18.02 AMU. Since 1 mole of H2O contains 2 moles of hydrogen and 1 mole of oxygen, okay, so now that we've multiplied the number of atoms by a mole, we also multiply these by it, and the proportions stay the same. That's going to be important in the next part. Now the molar mass of 1 mole of water is equal to 2 times 1.02 grams. So now we're placing AMU with grams, plus 16 grams. So 1 mole of water weighs 18.02 grams. 1 molecule of water weighs 18.02 AMU. So it extends out just like it did for the case of elements, where AMU is equal to grams per mole. The important thing to realize is that this is now an additional step we're always going to have whenever we have a molecule in our calculations. So let's see how that plays out. So now if we want to calculate the mass of 1.75 moles of water, the first thing we need to do is recognize that this is a molecule. So we're going to have an additional bit of work to do. We're given that we have 1.75 moles of water, just like as we were before. We're asked for the mass, just as we were before. And our solution map is the same. The difference is we now can't just go straight to the periodic table and look up the mass of water. We have to look up the different parts of water and calculate its total mass for that guy. And then we can write out our fact that 1 mole of water is 18.02 grams. We can convert that statement over to a conversion factor. Once again, I keep mentioning it because it's important. We're going to make sure that we put the grams in the numerator and the moles in the denominator, because we want to cancel those. We want our final answer in grams. We plug it in, and the math works out just as the same as it did for elements. 1.75 moles of water times 18 grams for every 1 mole. We'll cancel those moles, and we'll round to the appropriate number of sig figs. Let's look at our check. Since the given amount is more than 1 mole, the mass being greater than 18 makes sense, right? We had almost 2 moles. We get almost double 18. So let's see if we can go the other way with this. If we are given the mass of a molecule, can we figure out how many moles that is? So we're given that we have 50.0 grams of lead oxide, and we're asked for the number of moles of lead oxide. Our solution map is just the reverse of what we had before, right? And we need to calculate the overall formula mass for lead oxide, okay? Do not forget to multiply by things like oxygen when you have 2 of them present, as indicated by the subscript, okay? And don't let it sway you if your periodic table has slightly different values than that. The problems that we have allow for that, so you should be fine. We have our statement that 1 mole of lead oxide is equal to 239.2 grams. And we have a conversion factor here that 1 mole of lead oxide for every 239.2 grams. Okay? Once again, we're being careful about which unit we have in the numerator versus the denominator. We plug her in, and we get a pretty long number of moles here, but we're limited by these 3 sig figs. We get 0.209 moles of lead. We check our units. We can see that grams canceled, and we should be getting moles out, which is what we wanted to get in the end. We do our check. We were given an amount that was less than 1 mole, and so therefore it makes sense that we got less than 1 mole. Let's do one of the combined problems that we had before. All right. So now we're talking about how many formula units. You'll remember that lead oxide is an ionic compound, and that the formula unit is similar to the idea of the molecule. It is the smallest repeating pattern within that ionic structure. Okay. So this is analogous to us going from mass to atoms of an element, only now we're going from mass to formula units of an ionic compound. We already know that lead oxide is 239.2 AMU from the previous problem. So we're given that there's 50 grams of lead oxide, and we're asked to find the formula units of lead oxide. Again, our solution map has moles as an intermediary. We can go from mass to moles, moles to units, but we cannot go straight from mass to units. All right, just like we couldn't go from mass to atoms, we can't go mass to formula units. We have our 2 facts. Again, if we did not know from the previous problem that lead oxide was 239.2 grams, we would have had to calculate that. And we have our 2 conversion factors. We have 50 grams of lead oxide. There's 1 mole for every 239 grams. There's 0.062 times 10 to the 23rd units for every 1 mole. We'll cancel those grams. We'll cancel those moles. And we see that there's 1.26 times 10 to the 23rd units of lead oxide. Now we started off with less than 1 mole's worth of mass. So it makes sense. Then we've got less than 1 mole's worth of units out of it. Let's do one more where we go from mass to No2 molecules, just so that when we change up the language between ionic and molecular compounds, that we're not swayed by that. So we're given this many No2 molecules, and we're asked to find the mass. So this is going to be the reverse of the last problem where we were given the mass and then asked to find the number of molecules. But again, we're not going to let that sway us. We're just going to reverse our solution map, and we're going to realize that again, we have to use moles as the intermediate between molecules and mass. We'll need to know how much an No2 molecule weighs. We go to our periodic table, add them up, we get 46.01 AMU. Now we have our 2 facts that we're going to need for each of these steps. We know that 1 mole of No2 is 46.02 grams, and that 1 mole is equal to 6.02 times 10 to the 23rd things. Going from molecules to mole, we will use this guy, make a conversion factor there. Again, we're canceling molecules and we're getting out moles. And then we'll use our conversion factor here, where we cancel our moles and we get out our grams. Putting this all together, we get 4.78 times 10 to the 24 molecules of NO2. That was given to us in the problem. We apply our first conversion factor. We can cancel those molecules. We're now in moles. We can cancel moles. We get out our mass. And we wind up with 365 NO2 molecules. If we do our little check here, since the given amount is more than Avogadro's number, right? So now we're at 10 to the 24, where Avogadro's number is 10 to the 23rd. So we're at least 10 times high. We're almost 10 times higher now. It makes sense that we're at a greater amount than 1 mole's worth of mass, 46 grams, right? So now we have more mass than 1 mole's worth because we have more than 1 mole.